This video is part 2, covering material from section 7.8, improper integrals. In the first video, we looked at this first objective, find integrals with an infinite limit of integration, and really the second objective, interpreting improper integrals geometrically. That is, we can talk about the area between the curve and an x-axis, or as we originally said, under the curve of a non-negative function. And even though this region was infinite, we can talk about the area being finite if the integral is what we called convergent. In this section, we'll look at predominantly the last two objectives, integrating functions over some closed interval that have a finite number of discontinuities, a finite number of infinite discontinuities, some vertical asymptotes somewhere in that limit of integration. The objective here talks about specifically at an endpoint, but we can actually loosen that to be anywhere within the interval. And then hopefully we'll get to see the use of the comparison test for improper integrals as well. Alright, so this second type of improper integrals that we want to look at are integrals of functions that become infinite, have vertical asymptotes at some point within that interval of integration. Now, we're going to focus mostly on the two endpoints. If the function f of x is continuous on this half-open interval, half-closed, half-open, clopin, I don't know what you want to call this, but from a to b, including b, but it's discontinuous at a. That's why we have an open parenthesis at a. We have some vertical asymptote at x equal a, but it's continuous for all other values of x in the interval from a to b. Then I can talk about the integral from a to b, but for that lower limit of integration a, that letter a I've got to replace with some other letter. I'm going to call it c, since a and b are used. And I want to take a limit as c approaches a from the right. So c is somewhere in between these numbers a and b, and c is getting closer and closer and closer to a as it approaches from the right-hand side of a. So we take a limit as c goes to a from the right of this definite integral. Same thing if we look at the interval from a to b and we have the discontinuity at the right endpoint, where we have a vertical asymptote at the right endpoint. We're going to take that integral from a to b, and I'm going to replace that upper limit of integration, replace that letter b with some other letter. I'm going to call it c, and we're going to take a limit as c goes to b from the left, right? So c is somewhere in between a and b, and it's getting closer and closer and closer to b as it approaches b from the left. If the point of discontinuity is somewhere in the middle, right, somewhere between, some point c between a and b, somewhere in the middle, then we're going to split this up into two pieces, and each of these two subintervals we're going to handle with the case up above. So the integral from a to c, where c is an infinite discontinuity, that would be case 2. And the integral from c to b, where c is the infinite discontinuity, that would be case 1. So just like we did for the first type of improper integrals, we're going to maybe have to split this integral up, split the interval up, split the integral up, right? In this case, specifically at the point of discontinuity. In the first case, it was at a point of our choosing. All right, just like before, if we take this limit of this integral that we did and the limit is finite, then the integral converges, and if the limit fails to exist, either the limit is equal to plus or minus infinity, or it fails to exist for some other reason, then the integral diverges. Alright, let's take a look at our first example. We want to evaluate the integral from 0 to 1 of 1 over the cube root of x. Alright, we notice that 0, right, in our interval of integration here, 0 is a place where the cube root of x is undefined, right? I can't plug in 0 for the cube root of x. So this function has an infinite discontinuity at x equals 0. So I'm going to replace that place, that part of the definite integral, that lower limit of integration, with some number. Again, since I called it c before, I'll call it c now. It doesn't really matter what the letter is, as long as it's not x. All right, I'm going to take a limit as c goes to 0 from the right. All right, c is some number between 0 and 1. It's approaching 0 from the positive side. Take a limit as c goes to 0 from the right. The integral from c to 1 of x to the minus 1/3. Of course, that integral isn't so hard. We can do that. we get x to the 2/3 divided by 2/3. We're going to evaluate by plugging in the top minus plugging in the bottom. And I've done some cleanup here, right? Dividing by 2/3 is the same as multiplying by 3/2. So I pulled the 3/2 out. I plug in 1 minus plug in c. And I want to take a limit as c goes to 0 from the right. Of course, that's nothing more than taking 0 and plugging it in for c. So the limit as c goes to 0 from the right of 1 minus c to the 2/3 is 1 minus 0 to the 2/3, or 1 minus 0. Or in other words, this integral is 3/2, which means the integral converges, right? It equals a number. Had the integral equal plus or minus infinity, or had the limit failed to exist for some other reason, then the integral would have diverged. But this integral converges. The limit as c goes to 0 from the right of the value of our definite integral is equal to a number. Therefore, the integral converges. Okay, our second example, we want to integrate the integral from 0 to infinity. We want to evaluate the integral from 0 to infinity of 1 over the square root of x times x plus 1. All right, now we have a couple of problems here. We notice first off that our upper limit of integration is infinity, and our lower limit of integration is 0, and I can't use 0 in my function. 0, the square root of 0 is 0, so it puts a 0 in the denominator. So I've got two problems in this integral. So what I'm going to have to do is, even though it's two different types, one of them has an upper limit of integration of infinity, the other one has a lower limit of integration where the function is undefined, right? Even though it's two different types of improper integrals here, I'm still going to have to split the integral up just like I did when there was two of the same type. So for lack of a better place to do it, I'm going to split this integral up at 1. Doesn't really necessarily matter, but 1 seems to be a nice convenient place. 1's easy to work with. So until I know better, that's where I'm going to split it. Now I'm going to try and integrate each of these, but of course the first integral I need to replace the lower limit of integration with a limit, and the second integral I need to replace the upper limit of integration with a limit. So, and I'm going to do a substitution while I'm doing this to integrate this function, 1 over the square root of x times x plus 1. I'm going to do this with the substitution u equal the square root of x. So du would be 1 over 2 root x dx, or in other words, 1/2 du is 1 over the, 2 du is 1 over the square root of x dx. Alright, putting all that in place, right, 2 du is 1 over the square root of x dx. X, if u is the square root of x is u squared. And then I replace my limits of integration. I take a limit as a goes to infinity, the limit as a goes to 0 from the right of the integral from a to 1. And then I take the limit as b goes to infinity of the integral from 1 to b. Now both of these integrals, right, they have the same function in here, so they're going to have the same antiderivative. That's 2 tangent inverse u. So do the integration, or arctan u if you prefer. Do the integration, plug in the top minus plug in the bottom for each of these, and then we're going to need to do, I undid because I kept the limits of integration in terms of x. I had to get back in terms of x before I plug in top minus plug in bottom. So we did that. And now on the next slide we're going to plug in the top number minus plug in the bottom number for each, and then take a limit. So here's where we were on the last slide. We want to plug in top minus plug in bottom for each one. So I plug in 1, square root of 1 is 1. Plug in a, that's the square root of a. Over here, plug in b, that's the square root of b. Plug in 1, the square root of 1 is 1. And I'm going to take the limit of each of these pieces. Take the limit as a goes to 0 from the right. Take the limit as b goes to infinity. And when we do these, well, I can evaluate tangent inverse 1. Tangent inverse 1 is pi over 4. When I take a limit, I'll be evaluating the tangent inverse of 0. Tangent inverse of 0 is 0. Tangent inverse of infinity, so to speak, that's pi over 2. And of course, we already talked about tangent inverse of 1, that's pi over 4. So plugging all of these things in, right, we see that we get 2 times pi over 4 minus 2 times 0 plus 2 times pi over 2 minus 2 times pi over 4. All of this simplifies out, and our answer is pi. So this integral converges. All right, one last topic we mentioned from the objectives for the section was to be able to use this this convergence test, basically. And we're going to use this if there's some reason we can't evaluate this improper integral. What we're going to be able to do is using the techniques from 7.6, we could approximate its value using some numerical methods. But if we don't have access to those techniques, all we really want to know is whether the integral converges or diverges. And the way we can do that is through this thing called the comparison test. All right, here's the comparison test. Let f and g be two non-negative functions that are continuous on this interval from a to infinity, where f is always bigger than g over the entire interval. So f is the bigger function, g is the smaller function. If I know that the integral of f, the integral from a to infinity of f, converges, so if I know the bigger one converges, that is, this integral is a number, then I also must know that the integral of the smaller one must converge. Think about this. F is bigger than g, so if I take the integral of both pieces of this inequality, the integral from a to infinity of f is a number. So the number has to be bigger than or equal to some other number here, so that means this integral must also converge. On the other hand, if the integral of the smaller one diverges, if the integral from a to infinity of g is infinity, well, f can't be a number because f has to be bigger than g, so the integral from a to infinity must also diverge. So if we know something about the convergence or divergence of one of them, then I might be able to determine the convergence or divergence of the other. Notice there are times where it's not going to work. If I know, for example, that the integral of g converges, that means this integral is a number. Well, the integral of f might be a number or it might be infinity, because infinity is bigger than 6. Right, so there's no guarantee if this converges, doesn't tell me anything about f. If it diverges, then I know f diverges, the integral of f. Similarly here, just knowing that f, the integral of f diverges, tells me nothing about g. Infinity could be bigger than infinity, or infinity might be bigger than 6. So I have to make sure that it works the right way. That if I know that the bigger one integral converges, it forces the integral of the smaller one to converge. And vice versa. If the integral of the smaller one diverges, then I know the integral of the bigger one must diverge. All right, one example, and we'll end this video. I think one example might be enough to kind of prove the point here. We want to determine if the integral from 1 to infinity of 1 over x squared plus 5x plus 1, whether or not that converges or diverges. I'm not actually going to compute the value of the integral. I just want to know if it converges or diverges. Well, I notice that 1 over x squared plus 5x plus 1 must be less than or equal to 1 over x squared. And it certainly must be positive. So if I know that 1 over x squared plus 5x plus 1 is less than or equal to 1 over x squared, I also know that the integral from 1 to infinity of 1 over x squared converges, right? I had a theorem a little while ago on video 1 that told us that for all values of p bigger than 1, in this case 2, is bigger than 1, I know that this integral converges. So I know that the integral from 1 to infinity of 1 over x squared converges. It equals some number, whatever that number is. So this one here, the one I'm interested in, when I look at integral from 1 to infinity of this function, it must also equal a number that's less than or equal to this one's integral. Therefore, it must also converge. I used the wrong word there. Right? If we're less than something that converges, I must converge. Right? That's how this test works. We are looking to integrate a function that I'm not sure how to integrate easily, and all I really care about is whether it converges or diverges. Then I search for a comparison function that I know converges or diverges that has the proper relationship. In this case, I'm less than something that converges, therefore I must converge.